everyone, welcome to the Biological Society Young Person Sector Competition. Just to introduce myself, for those that don't know me, I'm Leonardo, Systems Engineer at Leonardo, working here for nearly 2 years now. But tonight I will be the host of the Biological Society Young Person Sector Competition, where we have 6 fascinating and very nervous competitors in front of us. So I'll ask politely to introduce themselves.
Hello everyone, I'm Alex Bates. I'm a current graduate at NVDA, working as a test architect. I'm here to talk about why aviation museums deserve our help.
Hello, I'm James. I'm also from NVDA. I work as a materials engineer, and I'll be talking about the degradation and migration of stabilizers in double base propellants.
Hello everybody, my name is Joanna. I'm a mechanical engineering degree apprentice at RAeS Defence and Space, and I'll be talking about the future developments in space technology.
So I'm Adam, I'm a second year electronics degree apprentice here at Leonardo based in Luton. I'm talking about physics spectrum in 2025 and beyond.
Hi all, William Nichols. I'm an Airbus final year degree apprentice, and I'm going to be telling you a little bit about supersonic aircraft and going beyond the sound barrier.
Hello everyone, my name is Leonardo. I'm a systems industrial placement student at Leonardo. Today I'll be talking to you about the growing threat of orbital debris and Kessler syndrome.
Thank you very much. Very exciting. Looking forward to it. And to judge our 6 competitors, we have some of the industry titans to judge. So if you'd like to introduce yourselves.
I'll kick off. Yeah, kick off. So, hi everybody. I'm Tony Chesbury. I used to work on this site up until about 4 years ago when I retired. I've kept active in the industry though. I work helping out with the Aeronautical Society as of tonight, and also encourage those that are retired to come and join the retirement club as well. So it's been a great experience this site. You boasted 2 years, I can boast 52. And that covered a wide spectrum of work in terms of originally guided weapons, design and engineering guided weapons, went on to radar systems and changed companies to Marconi. And then in later years, I went on to sensors and EW. And then for the benefit of probably traveling the world, seeing all the world with what was export work across many different programs and projects. So great place to work. Here, NVDA and Airbus, I've worked all those 3 sites.
Okay, in which case I'll hand over. So, hi everyone, I'm Steve Trimble. I'm the Vice President of Engineering here at the Luton site for electronic warfare for Leonardo. So I'm a fellow of the Royal Aeronautical Society. I'm a member of the Institute of the IUT, as I'll make it easy. So I'm a very active member within the institutions, and I also chair the mentor council here for all of the institutes within Leonardo. That's for the UK. My background, so I started off in the Royal Air Force back in the mid-80s as an avionics engineer. From there, I left there, went to the Defence Research Agency. So I was in the research world for going on for 6 years through that 6 transitions that went into what's now in DSTL. So working with those guys. From there, I went to work for US firms for a little while. Into Goodrich Aerospace in the ISR world, doing long range optics for the U2, Global Hawk, F-15, F-16, a lot in that arena. Moved to the US then in 2012, working for those guys. And I then went into the space world, worked in the ISM space domain. And my last role there before coming to Leonardo was running software for all of Collins Aerospace. One of my favorite programs there was developing the new spacesuit for the ISS. So that was one of the programs in my portfolio was the orbital life support system for that, which is not hugely technical, but you can imagine the criticality there and the precision you have to have in that is like intense. But yeah, so it's been here now 18 months, and it's a great place to work, and it's great to get to come back to the UK and work with such great people. And let's say enjoy yourself tonight. This is it's important.
Thank you.
Yeah, so I'm Bob Baldwin and I'm a CNG MI Mechie. I've been doing space propulsion for 45 years at Stevenage, so it was first British Aerospace, now Airbus. And I did 20 years on telecom satellites and then the last 24 years on science space telescopes. So I think one of my proudest achievements is working on the Gaia spacecraft, which has just recently been deorbited. Yeah, so I've had a really good long career, and in 2024 you could see my certificate. I won the BIS Arthur C. Clarke Award for Lifetime Achievement in Space Propulsion.
Good, thank you very much. Thank you, judges. Now, for everyone's information, all our competitors today will be competing for the Royal Aeronautical Society Eagle. So whoever comes in first place will get to take this home with them and have their name engraved on it. So, no pressure. Each of our competitors will have 10 minutes to present their lectures, and following that, they will have 5 minutes of Q&A. First, the judges will ask their questions, and any time remaining will be open to the audience. So, everyone ready? Yes, all right. Okay. Will, would you like to take the floor?
Yeah, I'll put my microphone on.
Thank you. Do I have clicker or just on here?
Yeah.
Oh, sorry, I think it's going a bit crazy. I'm not entirely sure what it's done. It wasn't me, I promise. Okay. Thank you very much. Firstly, thank you for having me, and thank you for agreeing to listen to my presentation. I'm very grateful to both be here and have the opportunity to present to yourselves and the esteemed guests as well. So today I'm going to be telling you a little bit about supersonic aircraft and the aircraft which have surpassed the sound barrier and the technical challenges of doing that and the engineering feats that have been overcome since the 50s. So firstly, we need to establish what the sound barrier is, and quite simply, it's not a real barrier. It was once thought to be, hence it got its name. It was thought to be impassable, but what it actually is it's similar to how a boat leaves a wake as it moves through a body of water. An aircraft will leave a wake of both sound and air. So as an aircraft is stopped, it has a permanent emission of sound, and at subsonic speeds, it then slowly starts to overtake it, and this is known as the Doppler effect, which is common in sirens as they go past, and obviously sports cars and Ferraris and all sorts. You'll have heard the meow. So when you approach the speed of sound, the sound cannot physically move out of the way of the aircraft fast enough, and it reaches a high compression zone on the nose of the aircraft. This then conversely generates a low pressure zone at the rear of the aircraft. When it then becomes fast enough, the high pressure quickly moves to fill the low pressure, creating what we know as a sonic boom and a large Mach cone as demonstrated by this jet. The first aircraft to successfully create this sonic boom was the Bell X-1, and it was piloted by Chuck Yeager. He was an NACA test pilot, which has since become NASA, and the early design was actually inspired by a 50 caliber bullet. You can see, maybe if this projector was a bit brighter, you might be able to see better, but you can see the bullet itself is very reminiscent of the shape of the aircraft. And that's because the only supersonic thing they had to go off at the time in terms of design was a bullet. And that's because bullets are shot at, obviously, speeds in excess of the speed of sound. So the Bell X-1 was rocket propelled. It was closer to a missile rather than it was an aircraft. It had 4 chambers, each of which producing 6,600 newtons of thrust, which, although sounding like quite a lot, is only about 17% of a modern F-14 fighter jet and only 1.2% of a Raptor engine, which is obviously powering the latest SpaceX rockets. Chuck himself was a bit of a character. He goofed during a gliding test and engaged in a mock dogfight, much to the dismay of what is now NASA. And again, during his first propelled flight, he exceeded the allowed 0.8 Mach to go to a 0.94 Mach, which he discovered that all of a sudden his controls no longer worked. And that was because the shock wave, which we showed, actually propagated right in front of these control surfaces here, rendering them rather useless. So it was engineered that the control authority on the rear control surfaces would be given a greater section, and hence it could maintain its control at supersonic speeds. These findings were then recycled for the X-15, the X-1's successor, although by a different company, still spearheaded by NASA. It's the fastest man-made plane ever, if you could call it that. If the Bell X-1 was a missile, this is much closer to a rocket. It reaches 6.7 Mach, and it does so in a simple 85 seconds, in which time it has burnt 8.2 tons of fuel and oxidizer. So it's really good for one boost, and that's about it. The rear section, which we discussed, which was important for control on these supersonic aircraft, was actually so long on the lower section in order to maintain authority at high angles of attack that it must be jettisoned to actually land. So it was left and potentially recovered at a later date. But I always find it interesting when you watch the videos of them landing, they look like something's missing, and it's quite simply because they are. Another interesting fact about this incredible aircraft was that it was spray painted with a pink ablative material, which was designed to perish at supersonic speeds to take away some of the thermal energy, which is obviously imparted at these really high speeds due to resistance. They then sprayed over that with a further white material, controversially getting rid of the beautiful pink, but it can be seen as scars as it erodes. But the nasty side effect of that was it would cover the windscreens. So you can see just here, it actually wears a pirate's eye patch, which is closed for supersonic flight and then opens again once it goes below the supersonic threshold, allowing the pilot to actually see where they're landing. And I'm sure with that open, with the aerodynamics, it must be a bit like driving a car with the tracking out. I don't reckon that's a fun landing. The SR-71 is a personal favourite of mine, and it built upon those projects in later years. So the advantage of the SR-71 is that it could sustain supersonic speeds. So it was capable of Mach cruise. So it could go beyond 3.2 Mach or beyond 1 Mach at least without using the afterburners at all. And it did so incredibly comfortably and incredibly well, leading it to have an incredibly successful campaign evading missiles simply by going faster than them. And the reason it had such fuel efficiency is it uses a hybrid ramjet. So typical conventional motors, or jets rather, on a plane are very good at low speed, and then ramjets are very good at high speed. They used a varying nozzle which could change the aperture of the inlet to make it both compatible at both low speeds and high speeds, making it perfect for this use and application. And interestingly, due to the ramjet nature, it was far, far more fuel efficient on a cold day as the air was much denser. So we've discussed a little bit about the challenges of supersonic flight, the first of which being heat, which the SR-71 was particularly partial to, reaching a toasty 320 degrees across all of its surfaces at Mach 3+. And again, further thermal expansion as a result of this. The SR-71 famously used to leak fuel onto the runway as a result of its large panel gaps, which were needed to stop buckling during thermal expansion. As a result, they had to use an inert fuel. And that brings us on to our second problem, fuel consumption. The fuels which are ideal for these temperatures are not ideal for these speeds. And again, it's caused a plethora of problems over the years. The shock waves themselves affecting the control surfaces, and particularly where commercial applications are concerned, sonic booms. Going over densely populated areas whilst making sonic booms does make the news and does not make for happy residents. Bernoulli's principle will also further invert at supersonic speeds, therefore making the calculations nigh on impossible for the people at the time who were trying to predict this. Hence, they went off their best representation, which was the 50 caliber bullet. But it really does get beyond even modern comprehension of airflow when going beyond supersonic speeds. And again, the engine configuration, like I mentioned, that which worked at subsonic speeds does not work supersonic. The Concorde is by far the most famous supersonic plane, debuting in 1969. And it was funded by the French and British governments to the sum of 2.8 billion. It famously generated its lift using vortex cones rather than a traditional wing. Rather than having strong aerofoil lift, at high angles of attack, the delta wing, the OG curve, generated these large vortices above the wings, creating a low pressure region and hence generating lift. This means you can't see where you're going. So they put a droop snoot, as they dubbed it, on the front of the aircraft so that during landing at these high angles of attack, they could actually see where they were going. It wasn't all rainbows for the Concorde, however, as it still suffered from thermal expansion, meaning that at the end of a pilot's career, it became tradition to, at supersonic speeds, when everything has expanded, place your cap in between the instrument cluster, and then when you land and it contracts, it's then trapped there as an immortal memory of your career. We've talked about some of the problems with supersonic speed, and particularly the downfall of Concorde was to do with these residential booms. They caused masses of issues, and it was ultimately what led to it being non-successful, along with the fact that people no longer wanted to pay the increased prices and fares for what had ultimately become a novelty at the time. The Concorde was cramped and it was loud, and ultimately nobody's 3 hours is worth that much. Boom Supersonic, however, is trying to bring it back, and they do think there's a demographic for it. They're a US company, and they've developed a Symphony engine, which is supposedly both incredibly quiet and efficient, running on 100% sustainable fuel. They reckon that they can have mass savings over the Concorde by having 2 pilots rather than 3, with the use of helpful technology and AI. And already United Airlines have committed to buy 15 of their Overture planes. They don't, however, address how they're going to work around banned routes, how they're going to overcome range issues. And if you look at the design, there's a large lack of boom reducing features. And obviously, as I mentioned, it's a boom from the tail to the rear of the aircraft. And that is a rather long aircraft. And obviously the length dictates the amount of differential pressure and hence the amplitude of the boom. So I'm not too convinced yet, but they're definitely trying to win people over. Thank you very much for listening. I appreciate that was a lot of information, but I am very passionate about it and tried to get it out as quickly as I could. Any questions?
Hopefully I can do the answers.
Really interesting, Will. Thank you for that. Oh yeah, I've got to put the mic on, sorry. Yes, well, very interesting. Thank you. That very detailed presentation in what was a short space of time.
Thank you very much.
I've got one question is, what made you choose this topic?
Yeah, so I've got a deep set passion for supersonic aircraft. Those who've seen me around site at Stevenage, they know that I've got an SR-71 pin on my lanyard. Yeah, I really enjoy learning about the aircraft and then conversely the challenges that come with it. There's several documentaries which I find myself enthralled in on the topic, and yeah, it's been a passion of mine since. Thank you very much.
So my question is, so you showed some of the great aircraft that we had through, during back in the 50s that were out of the skunk works, and you look at that period of time where there was a real reason that we had the whole space race, everything was going on around that same time. And so funding for those programs was
3.2 billion.
Correct. Yeah. So do you think that these people, and we've already seen some of the people who were getting into this back in 2019, 2020 already go to the wall. Do you think the funding will be there for people like Boom to actually make it happen?
I think it's going to be a problem. I think Concorde succeeded as a result of its heavy financial backing, but I think the private sector will initially struggle. But if anything's been proven over the past few years in the industry that I work in, the space industry, it's now that private companies like SpaceX now have the advantage over more government-funded firms like ourselves at Airbus. So it's not unheard of that they can do it. They've just got to really find some clever solutions with the advantages of modern composites like carbon fibers. A lot of the thermal expansion issues that we talked about, they can mitigate those because it's not very thermally expansive. But whether they'll manage to do it in a time frame and whether there's still a demand for it, I think is the question on everyone's mouth.
Just one more.
Of course.
So we talk about supersonic. Do you think we'll ever get to hypersonic?
I'd like to think so in my lifetime, but I think it becomes a problem where everybody who wants to go hypersonic wants to do it beyond the Kármán line. And at what point does it become a rocket?
So I'm happy to hand over to the audience now.
Any questions for any of the audience members?
Yeah, just one. So supersonic's sort of a bit passé now, isn't it? So, the judges mentioned hypersonic.
Yeah.
So is there another perceived barrier above supersonic?
Not particularly. It's yeah, the threshold is one that we've made ourselves just to the limit of our thrust capacities and thermal capacities. If we could hypothetically use materials that could withstand those higher temperatures and boosters which could produce higher thrust, we can go as far until the next barrier where the air density becomes too high or too ablative, where it starts destroying or superheating the materials.
Any further questions from the audience? I have one question.
Of course.
What boomer's features is missing from the boom supersonic
In
aircraft?
terms of boom reduction.
Yeah.
So obviously they've got a rather long aircraft, and NASA have recently developed almost an intake scoop on the top. And what that actually does is it encapsulates the boom at the point of boom. And because it's a conical shape, it breaks up the cone, which greatly dissipates the sound wave itself. So it almost bounces it outward and around the rest of the aircraft, which obviously reduces the decibels as it covers a broader range.
Thank you.
Thank you.
Thank you very much.
I believe that should just still be on. It does look green.
Yeah. Oof. That's not what I
Yeah,
wanted.
oh, there it
Oh,
is.
there we go.
Took a second. Okay. So, hello everyone. Just for anyone who's joined, just as a quick reminder who I am. I'm Alex Bates, work as a graduate at MBDA, and I'm here to talk about why aviation museums deserve our help. Not just need, but deserve it. So, first off, if I can figure out how to work this. There we are. I wanted to ask just a question to the audience. When was the last time you went to an aviation museum? I mean, just to answer this myself first, for me, that was about 6 weeks ago. I went to the de Havilland Museum just down south. Is anyone else? Feel free to shout out, raise your hand.
Shuttleworth last week.
Shuttleworth, very nice. Okay, so a good range is what I'm hearing about that. And what did you feel when you went to those museums? Why did you go in the first place? Inspired, inspiration, and that's kind of the key thing that I want to promote here, is why we need to care about these museums, because they've got some of the country's greatest heritage and achievements here. And it's not even just the country's heritage itself, it's people's livelihoods, design engineers, manufacturers, operators, technicians, everyone down to who soldered the last pieces of wire had a part of this aircraft's history within it. And it needs to be talked about, it needs to be remembered, because these things are just too important to be lost to time. And so I personally want to try and continue this. And that's why I'm obviously here today to talk about it. But first, why should you yourselves care about it is kind of the key thing, aside from what I've just talked about. You have fountains of knowledge here. You have experts who have worked on it for decades, who will just talk your ears off for hours on about these aircraft and everything surrounding them. And they will always be happy to converse with anyone interested. And at the end of the day, they're fun. That's why a lot of people do these things, go to museums. It's fun to just learn about the past, learn about people's experiences from what's gone on. So what's actually happening with museums currently? At the moment, there's a big push for restoration, actually. I mean, most of you, hopefully, in this room should have seen the flyover for VE Day with one of the only 2 Lancasters in the, I believe, the world actually able to fly. That's all because there were people, volunteers out there, who sat down and worked on this aircraft hours upon hours upon hours to get it ready for something like this. And to be able to show off that work, to me, it's something we need to both praise more and get involved more as a society. There's also recently been quite a big push from both government and the personal public sector for STEM and museum interest. And the issue here we have is there just sometimes isn't enough volunteers to do it. We have people spending a couple hours here, a couple hours there, and they've had to sit there and talk to so many different variations of people, and there just isn't enough support for what they need to be doing. And again, it's an aging population brings kind of some unique challenges, I would say, but also some good opportunities, especially for those of us in the early careers, because these people who have worked tirelessly across their careers on these aircraft have that fountain of knowledge. There were processes of ways things were done back in the day that these people only solely know because they were there when it happened, and only by interacting with them and actually working alongside them can we actually, in my opinion, effectively get this transfer of knowledge. And so while I was doing a bit of research on this topic, I personally am a bit of a nerd myself, and I came across the quote from A. Heinlein, who was both a sci-fi author and also worked as an aerospace engineer during the Second World War. And so I think it portrays this quite perfectly of a generation who ignores history, has no past and no future. Because volunteer doesn't just mean you help out, you become a part of the museum's history. You get ingrained in its soul, in its memory. Volunteers who come after you will remember it. People you interact with, children you inspire, will remember you and the experiences that you've imparted on them. You also, yes, like I said, get to inspire the next generation and also learn from the previous one. They're here and we're all human. We all have a finite amount of time. The thing that isn't finite, if we continue it, is knowledge and understanding and experiences. We can pass those on and keep everyone learning from it. And again, just furthering your understanding, the industry's heritage, the work that we have all done has only come about in the past 100 or so years. There's been so much, a fountain of knowledge that has been poured into this sector. And at the end of the day, it's only going to keep getting faster. So we need people to be able to maintain the pace and keep up with all the work that's been going into it across the course of this century. So, going a bit more into a technical side here, I think aircraft restoration and museums need you. Now, why do I think that? That's because not only do you preserve some history while becoming a part of it yourself, you also get to gain some practical skills. Now, a lot of people, I know the society is involved with a lot of universities and the course of accreditation. And as part of that, there is actually a requirement to have workshop training. And this is something that volunteers do on a day-to-day basis. They get involved with this kind of work. They're in the shop either restoring it or completely rebuilding it, machining it, hands-on for hours on end, and get to just enjoy everything. And it always answers the age-old question of, how did they do that? You look at, say, for example, the De Havilland Museum. You have some of the first instances of composite materials with the plywoods that they used for the Mosquito. Again, this is information that, well, yes, the internet exists, but the people who were there and did it by hand won't exist after the internet. And I think it's really important that we keep maintaining that and keep continuing that. Now, what do we think you need to do to get involved? I've talked a lot about kind of the key aspects of the restoration, what is important, and the interactions with the public, but who thinks they know what you need to do to get involved? contact them. That would be a good start. But I was more going with, you need to do nothing. In a sense of, you need no skills, no training whatsoever. All of this is on purely voluntary basis, and they require 0 qualifications to get involved with. You can get involved with the outreach, the events planning, the financial side of things. You could also even get involved in just groundskeeping, in tending the gardens. Now, you do need to be 18 plus to get involved, specifically with whenever you're dealing with anyone in the public. So at tour guides, anything like that, just because safety hazards and with working around children, that is a legal requirement. And I believe for restoration, prior experience in machine and aircraft maintenance is a bonus. It's not necessary, it will help you out. But museums will train you on these things. They will bring you up and upscale your knowledge in line with what they expect from their specialists so that you can actually continue this work and further it for your own personal benefit and the benefit of all of the attendees. So, which ones are looking for volunteers? Because there were quite a few museums in the UK, especially aviation ones. It's actually all of them. There is a massive deficit of volunteers across the entire UK, especially after COVID. And getting young people involved, getting them talking, learning from all these industry leaders who have spent their time and have enjoyed their livelihoods through this aircraft is just a wealth of opportunities that I think we all in here need to just grasp and be able to grab a bit more clearly and faster, if I'm personally honest. And so I just wanted to give some closing remarks, because as I was getting ready for this presentation, I thought about talking to some of my co-workers who are in the industry and some friends I know who have done some work, and I thought I'd get their take on it. And so someone I worked with often takes their son to Duxford because it's a beautiful place. It has a special place in my heart as one of the biggest sites in the UK, but also the fountain and wealth of everything that is there is just incredible. And museums they give the ability for people to connect with their history. If you work directly on the projects as well, you actually get to see everything. You would see someone's old handiwork in the thing you're restoring, which to me is that's an experience like no other, personally. But all in all, I think I've took up enough of your time here. I've given, hopefully, a little bit more clearance into why I think you need to get involved. And all I can really say now is just thank you for listening and any questions.
Yeah, okay. I suppose, would you say the same is true for every type of museum?
Oh, 100%. There is, I believe there was a statistic, I did make a note of it here, that about 23% of the volunteers across the nation are age 65 and over. And to me, there needs to be an effort to get that number down in the sense of getting more volunteers just into the whole sector itself. We need young people to get involved because at the end of the day, there needs to be a new generation after those that have passed on, and it needs to stay as an imparting of knowledge.
So just to say, it's encouraging to see somebody young enthused about our museums and about keeping our history alive. So as a classic car guy and who loves to restore cars, I see the same problem in that sector where it's hard to get young people to get involved in classic car restoration, and especially for older vehicles and older aircraft. When I can understand why it is, the older generation are more interested in restoring those. I was lucky enough to, I just remember the Shackleton still flying, yeah. And I also, when I first joined the Air Force, the first aircraft I worked on was a de Havilland Beaver. Yeah.
Ooh.
And so that was, the Army Air Corps were still flying just before they went to the Islander. But what is it for you that attracts you to the historic aircraft rather than, that's what I'm saying, because I'm trying to understand how we can get younger people better involved with it.
Personally, I find it a way to reconnect with our history. In my day-to-day life nowadays, I find a lot of times, if I ever need to go look something up, or if I never need to learn something, you just use a computer, you go on the internet. But growing up, I always would go, because I grew up quite close to RAF Cosford, I would always go there with myself and my dad to learn about this history. It's essentially, yeah. It's a fountain of knowledge that I will gush about it on and on, honestly. It's something that has always been a personal passion of mine. And to go around the country and see some of these museums either needing more volunteers or struggling to kind of bring in more support, it breaks my heart.
You were spoiled. You had the TSR2 to look at.
I did, yeah. No, I was a bit spoiled there, I won't deny.
Alex, thank you for that. With your obvious passion for historic aircraft, have you a standout pioneer or designer that you relate to?
Oh. Now, personally, I would probably say Whittle, which I'm aware isn't an overall aircraft design, but more obviously the engine manufacturing. And that is just because I have a personal love of aircraft engines, etc. From going from in 50 years from rotary pistons to the jet age, that has always been kind of my bread and butter as part of that. And I see Whittle as one of the key pioneers in that sector.
Thank you.
You're welcome.
Any questions from the audience? Question, if you don't mind. Obviously, you've been to a lot of museums and you've absorbed a lot of this knowledge through your history of attending them. I would say you can see in museums more nowadays a trend towards, if I call it more appealing exhibits or friendly exhibits. Do you think there's a balance to be struck between the depth of knowledge and the kind of accessibility? How do you see that balance, and do you think you sacrifice one to do the other to make?
I think there is definitely a benefit of finding that balance. As museums travel through time, they're going to need to innovate, they're going to need to adapt to current social norms that we're all used to. But part of me feels that there still should be at least some standalone museums out there that can cater to something that's a bit more old school, or something that's a bit more what it's like back in the day, and have both the option of perhaps the big ones, so your Duxfords, your Cosfords, your Hendons. They're more generalized because they will obviously see much more of the population, in my opinion. Well, I say in my opinion, I believe across those three alone had 1.2 million visitors last year, which it's not an insignificant number, I would say. And so having them be a bit more balanced, I think would be quite a bit better, but still having the more nuanced ones, the smaller, more local, that have a rich history in the area, those can stay a bit more kind of to their roots, in a sense.
Specific local connection.
Yeah.
Thank you.
You're welcome.
Okay, thank you very much.
Thank you for having me.
There we go.
HDMI from this.
Cool. We're all good to go. I'll begin. So, good evening. It's a great pleasure and an honour to be able to present this evening for the Royal Aeronautical Society Young Professional Lecture Competition. My name is Adam Huddleston, as I've been introduced. I'm a second year electronics degree apprentice here at Leonardo, based in Luton. And we're going to kind of get a flavour of what potentially that experience so far has been like throughout this. But I'm delighted to be able to present my lecture, Splitting the Spectrum for 2025 and Beyond. It's a typical kind of history walkthrough. And we'll begin. The inspiration for this lecture really came from this image on the left. I've recently become a fully licensed radio amateur in the UK through Ofcom. I'm also an early careers professional in EW, as I've alluded to. This image on the left was very striking for me. The IARU, IWS, formerly the IARU MS, try saying that 3 times fast, the monitoring service for the International Amateur Radio Union. They monitor non-amateur transmissions in amateur bands. This on the left, coincidentally, a whole range of radio jammers. Quite a stark thing to see with spectral and PRF information to boot in that unclassified document. Quite the wake-up call for me. It's quite a striking thing to see. What it really got me thinking about was 2 questions. How do we achieve non-interference? Obviously, these are interfering in that frequency allocation. What does the future of interoperability look like? And also kind of how that got me thinking about my views of band plans and aeronautical mobile allocations and where that picture might be moving. I've got 2 diagrams here. They're quite simple. It's looking at kind of the governance on both sides. I'm bringing in both a civilian aspect and also kind of a little bit of my early careers knowledge in that EW kind of more military aspect, and where there might be differences and where there might be overlap. On the left, I'm essentially bringing this down from the international level to a continental level to a national level, and some of those deliverables, again, the IARU, the amateur radio aspect of that side, the ITU, the International Telecoms Union, and the international side, bringing that down to continental aspects such as Eurocontrol and the FAA, and then some of their deliverables, their programs, CESAR, which I'll come on to in due course, next gen, and then one of the biggest deliverables of that being VDL mode 2. Again, we're going to come on to that in due course. On the right hand side there, looking a little bit more generally from a military aspect, keeping it all perfectly unclassified. So NATO, kind of, your general departments there, forward defence, air forces, and TDLs. I'll keep the acronyms to a minimum. Here we kind of see the general picture of what we're looking at when we talk about frequency allocations. Pages and pages and pages of lists of frequencies, who they're assigned to, how you can use them, the modes in which you're using in those frequency bands. Here you can see on the left, the well-known RSGB band plan for 2025. That's the one that I'm most familiar with. And it was seeing actually as well, combined with that IARU, combined with that IARU monthly proceeding, that really got me thinking about how we use the frequency spectrum in an increasingly congested EM environment. In the middle there, you've got from the ITU, the International Telecoms Union, as I've alluded to, their band plan, and on the right there from the IARU in Region 1. So that's kind of Europe and the Western world. Again, you can kind of see just the range of information there, and it's really interesting to think about how we kind of split that up in a way that makes sense, where those frequency trends might be going to. As I progress on to the past, a very short history of different things happening here. This incidentally on the right, again, taken from an interview from some pop journalism, military embedded on there. On the civilian side, we kind of start a little bit from the US here, from a particular article that I was having a look at, and the rise of line of sight VHF comms, and kind of the way that came about through the negotiations, incidentally here with ARINC, the Aeronautical Radio Incorporation in the US, and how the pioneering of VHF line of sight comms brings into focus night flying and instrument flying rules in the US at that time, and how those frequencies were allocated based on essentially who was flying the most miles. Sir, I'm flying 2,000 miles this year, please can I have this frequency? Is the kind of discussions that you see from the ARINC proceedings in the history. It's quite the read. On the right here, a very brief overview really from the history of an interview here on the ever famous Link 16. I'll brief over it, but again, throughout this investigation, as I try to keep it unclassified at my best, it's quite stark the amount of information that's available on unclassified sources on the web. We skip to the present. You can see here one of the main programs on the civilian side from Eurocontrol is this SESAR, the Single European Sky with aerospace research. That is for delivering that Single European Sky project, introduced in 2009. It's their plan up until 2040 for interoperability for air traffic management. It's again looking at how we solve this problem of a congested EM environment. Flights, I believe from their report there, they're saying 2019 the peak, and as we approach 2024, 2025, the present day, the flight numbers are only on the rise in Europe. So SESAR, again, their project there for delivering that interoperability. They're looking at technologies such as LDAX, again, another acronym, the L-band digital aeronautical communication system. That's one of the deliverables they're looking at to replace VDL mode 2. Again, I will get onto VDL mode in due course. Again, next gen there, like I said, from that kind of governance and deliverable overview, the FAA equivalent to SESAR there. Again, just a picture, just to kind of break up the words. Again, you can kind of see a summary there of links in current use, somehow still available on the web. The future, I'm absolutely rattling. Let's just say we've got a whole load of stuff. And LDAX, as I'd said there, it's really that move from the technology we've seen at present, and then also what we might do to transition to things like LDAX. It's really taking it from the traditional air-ground communications and actually taking that through, as it says there, SATCOM Class B. I would go into the technical details, but unfortunately, I don't have that time. You can see here, yeah, I've kind of just listed off those sorts of things they're looking at, and it's really about how they bring their plans, into action. Of course, with Eurocontrol and the Single European Sky, 2009, 2014, you start to get towards how we can bring interoperability on the Horizon programme in light of some other political challenges. Yeah, and you've also got roadmaps again from kind of across the industries there. The STO, Science and Technology Trends, is certainly an interesting read for the roadmaps in that direction. Kind of the way in which these roadmaps might align is certainly an open question. And it's interesting, actually, as I highlight at the bottom of the slide here, from the IEEE DICE ban. It was a conference held this week, actually, in which they were talking again on this frequency allocation question. I think it really just shows how in the zeitgeist, if you'll excuse the German, this question really is. As I've rattled through these slides, we've seen essentially the length and breadth of roadmaps and band plans that are out there, and perhaps a little bit more information than we bargained for on the military side. But it's really important that we secure that future for robust and considered frequency allocations, harking back essentially to these discussions from ARINC in the 1930s of, sir, I would like this frequency, here's your top dollar, to a world in which it's an increasingly congested EM environment, is really important to consider. With that said, thank you very much for your listening. Any questions?
You can go. Thank you for that, Adam. Yeah, having worked on this site, and it's a subject that's talked about an awful lot, frequency allocation, congestion. Who's responsible for dishing it out?
Yeah, I think it's a great question. It's really a flow down, as we saw. it's really that flow down and kind of overlap, I suppose, from the kind of international band plan. At the end of the day, that flow down from the ITU band plan to the Eurocontrol, to Ofcom, to those applicable national bodies is kind of that flow down, particularly like I say on the commercial side. It's really on that side. It lies with the ITU. You will see, as I should know, as a fully licensed radio amateur, you will see that band plans can differ then on a country by country basis for amateur radio, and so that's actually something that's important to be aware of as well. It really depends on what level you may be operating.
Just a quick follow-up. It's almost the commercial allocation versus military. And I was trying to indicate, should there be a priority there?
Yeah, I think that's also a great question. I think it's interesting. It's kind of the crux of this lecture. You know, how do we allocate those frequencies in a way that doesn't say, I'm a military organization, I'm using these frequencies and therefore nobody else can use them? How do we allocate those frequencies in a sensible way that provides that overlap, but doesn't give sensitive information, frankly? I think certainly as the world kind of looks forward into the next 20 years, there's some serious decisions to be made about what that priority should be.
Okay.
So my question sort of leads on from that. So if we look at the future battle space, talking the military piece, and there is this aspiration, the future battle space, everything will be connected. Yeah, you'll have that connected battle space. Every LRU will have its own IP address on that network, and we're going to have continuous integration, continuous deployment of software onto these LRUs in the air, in space, wherever we are. Will we be able to allocate the bands to make that happen?
Yeah, I think at the end of the day, the crux of that is that the EM spectrum is for most practical purposes not infinite, and that's really where this allocation problem comes in. I think that as far as kind of on the fly allocation goes, kind of administrative procedures in order to make people aware really has to kind of think deeply about how we're going to speed that sort of thing up. The ITU has a World Radio Conference every 4 years currently. That means they're reassigning frequencies if need be on a 4-year cycle. Realistically, if we're doing on the fly allocations, that's really not on the same sort of magnitude currently. So yeah, it's hard to see how that might happen.
Can you go back 1 or 2 slides?
Sure.
And one more.
Yep.
Could you just explain what we're looking at?
Yes. So on the left there, that's essentially spectral captures from radio amateurs who have tuned frequencies in amateur frequency allocations, and then plotted that spectrally, whatever they've received on that frequency. There's some extremely detailed reporting from these amateurs on exactly what these transmissions are, some of which I'm not going to go into because the fine line, as I've noted, is increasingly fine on those sorts of things.
What are the axes up and down and left and right? What are they?
So because it's spectrally, it will be, in fact, actually, some of these are time series, aren't they? Some of them are time series. So you can see so it will be time series of frequency. So essentially you can kind of see a pulse in transmission there on particular frequencies.
Okay, thanks.
Yeah.
Audience?
Any questions from the audience? Yeah, one of them. You mentioned about how these frequencies are becoming increasingly congested, and we've touched on how people sort of lay out their demands for the sections of set frequencies. Maybe it's an obvious question, but why are they becoming more congested? Why is it going up? Obviously, FCAS and such systems have been mentioned, but why is it so drastic now that it's becoming a problem now?
Yeah, I think the easy answer perhaps would just be the kind of volume of traffic. Again, kind of the request on each frequency and adjacent frequencies to a particular kind of mode is increasing. So like I say, like I'm kind of hinting to there, you know, worldwide civilian air traffic has been on the rise, of course, since the kind of end, perhaps you might say the end of COVID. But also kind of the range of technologies, you know, you kind of have allocations that are kind of set ad infinitum, if that's Latin and it's correct, forever and ever and for a day. But the amount of new technologies looking for new frequencies that aren't allocated for specific uses is also on the rise. You know, kind of looking for where is the next gap is what technology has to do. I hope that was somewhat of a coherent answer, and I do hope as well that my presentation has been more than just the ramblings of my passion. If there's any more questions, please do fire away.
Thank you very much.
Yeah.
Break, and then it's going to work again.
Thank you very much for this opportunity to talk about future developments in space technology. I am a third-year degree apprentice in mechanical engineering at Airbus Defence and Space. And recently I've been able to be involved in some strategic conversations about space technology and how the company is moving forward. So I thought this would be a great opportunity to just show off my knowledge a little. So 10 minutes is not enough to talk about every single thing that's developing in space, but we can talk about what's been happening so far. So as we can say, there is a lot of developments, there's a lot of launches, there's a lot of competition, there is a growing market for it. It's estimated about 2030, it's about to be about 1.8 trillion or something is supposed to be the space market. And so I wanted to focus on just a couple of main technology that might be useful for the future. And nothing's trade secrets, everything's mentioned, everything's fairly on the internet. I made sure to reference everything, so you have pages of reference if anybody wants to read afterwards. And also the technology mentioned here is not new. It's something that's been there for a long time, and it's just coming to market more often because engineering takes time. It takes time to make things good. So the first thing I want to focus on is quantum applications. So the first one is quantum encryption, cryptology. So in quantum, I can focus on two things. So there's PQC and QKD. So PQC is post-quantum cryptography. So basically that's, you have some mathematical information and that encrypts your information and it's very difficult to crack. Or you can have QKD, which is quantum key distribution. So each person has a unique key, and then that's how your information is encrypted. And these can be implemented on spacecraft structures, spacecraft platforms for the payload and for the ground information, because yes, it's important that information is encrypted between all platforms. And the EU is basically focusing on this. So the EUSPA, which is the European Union Space Agency is focusing on EuroQCI and SAGA, which are quantum applications for spacecraft applications. And on the right there, you might see an image of NASA's quantum sensing application. So then we move on to the next topic, which is quantum sensing. So we can talk about how gravitometers and quantum sensing is another main application for the future. So how you can have much more accurate, much more developed sensing on platforms, and doesn't have to be as it is at the moment. This is one of the concepts that NASA has come across with about a few years ago, and they've released it in a paper. So in terms of quantum, it is important as encryption and cryptology, as well as for sensing and gravitometers on board spacecraft. Now, the next thing I want to focus on is artificial intelligence and machine learning integration on payload. As you can tell, there's a lot of boom and noise about AI and machine learning, and it has important applications for Earth observation satellites, for example, to be able to detect the changes in forestry, to changes in litter, and how to even pick out specific types of plastic. The amount of Earth observation that increases and develops because of AI, of machine learning algorithms, is important, but it's also not new. It's something that's been done for years. In terms of, there's also applications for deep learning. So by ensuring that you have the AI to be able to detect and learn different patterns and to understand and to give that data back to us is also important. Now, collision aversion methods are also important to be able to tell the AI what might come in, because as we move on to the slides, we do talk about space debris as a main problem, and collision aversion methods through AI is also important to make sure that your satellite mission remains safe. But obviously these come with problems. It comes with limited onboard power, and it requires radiation and thermal shielding. So while you do have good technology, it does require a lot of infrastructure around it to be able to operate at the best possible level. Additionally, there are ethical and privacy implications of AI that you might infringe on. So it is also a slippery slope. So there has to be some conversations about that and laws that enforce it properly. And one of the other main focuses in spacecraft is going to be about in-orbit servicing and manufacturing. So on the right there is the Whisper Airbus arm, which was being tested in Westcott Space Cluster. So this, I think in-orbit servicing and manufacturing is something that should be also talked about, and how it's the ability to construct large structures, to be able to deliver bigger payloads in space without having to take up launcher space. Additionally, you can also reuse orbital platforms, so you can ensure that you can create orbital platforms in space for different types of on-board experiments to occur. And they are sustainable space architectures. They allow for reusability, and you can repair any structures that may be on board or up in space, but that comes at a cost as well. So it's like, how do you take that up? How do you make sure that the robot itself is working accurately, is doing what it's supposed to? So while there are some good things with all these technology, there is always some drawbacks. And now so we focused on just the three main ones, which is quantum, AI, and in-orbit service and manufacturing. So I didn't want to expand too much on different things, but I did want to also focus on future areas of focus that the space industry might focus on as it comes along, that things might change as we go. So the first one is materials digitization. So this was an interesting one as it came along in my research. It's that ability to make sure all material are from the supplier all the way to the end product, and you ensure that there's some reliability in the information you get. You can bring in new technology, bring in new materials, you can bring in every kind of new material, and there is some database and traceability of information, as well as the materials. You can also use powerhouse computing and new resources to be able to analyze your data much better, so that your materials data is much more up to date. You don't have as much testing to do. Implementing things like digital twins are important to ensure that you can do your testing, do less testing, and be able to rely on the computer much more. Another main point is the ESA's space situational awareness program. So that's basically as well as about orbital debris and stuff, and how that's a major issue. So you need to also, the ESA program is one of them among different countries, to find ways to capture this. So on the right, you have the UK government's one of the missions to, I think it's called Arrow or HARP, to make sure that you can capture space debris safely and make sure that it doesn't disrupt anything. That's another area of focus. And then the third point is space constellations. So there is an increase in space constellations, and as we can see, there is more funding for more commercialized spacecraft structures. So you might see more of the Starlink kind of satellites. But the issue with them is, obviously, we come back to the second point, is space situational awareness. It creates debris. It is fast-moving projectiles, essentially, for other spacecraft in the area, because in 2019, the ESA's project, AEOLUS had to move out of the way for Starlink that came in its trajectory. So it is a big problem that if you do have space constellations, yes, they are well-funded, they are there, but they are also huge problems in terms of space, within space. And the last point is about connectivity and data and processing infrastructure. So yes, you can have all the fancy stuff up in space that takes incredible images, but you also have to have sufficient infrastructure on ground to be able to take that information and relay it to the customer or whoever might be using that information. You also need to implement things like we spoke before about quantum AI into those infrastructure that allows it to be communicated in the best possible manner, for it to be in the best possible way set up for the consumer and for the company. Now, I finish this off with a quote from Mary Lou saying, "Everything's science fiction until someone makes it science fact." So yes, there is a lot of science fiction, but at some point everything was science fiction, but through a lot of engineering and hard work, everything becomes fact. Thank you.
Okay, I'll kick off this time.
Okay.
So we talk about a lot of the constellations you have up. There's a lot of, it's pretty congested there in space right now. So much of you talked about, I assume, as much as it's in the LEO. Yeah.
Yeah.
How important do you see GEO in the future?
GEO is just as important, and I think a lot of the bigger missions tend to go up to LEO, and a lot of the governmental missions and Earth observation ones tend to be GEO. But I think there's a bigger push to go to GEO because there is more space up there. So it is an important requirement to go up to GEO as well. See if we can use that. But obviously it takes more energy, it takes more power to get to that stage.
That was going to be my next. You see the challenge there. Okay, thank you.
Jana, thank you. Picking up on your slide on servicing and manufacturing in space, just thinking like the logistics and the responsive times for that, and it took us like 9 months to get a couple of astronauts back who were only supposed to be there for a couple of days, I think. So a couple of questions. How mature is that thinking, and are there any examples where we've done some realistic servicing and not manufacturing, but maintaining probably in space? Any examples you can think of?
Well, the big one is the International Space Station. That was a big in-orbit service and manufacturing example, and that was years ago. It is a big example, but it's just that it's not become as common to do that, especially on things like satellites and for small structures. But for massive structures, it is a big thing, and there would be a push towards, when the ISS is finally decommissioned, it would have to go through in-orbit service and manufacturing emissions as well, because you can't construct something as large as that on Earth. So you would see that happening again. And because of the push from the ISS, from the ISS decommissioning and replacing it, you might see more people trying to do that with different structures. So you might see bigger structures being built because now there's a means to get that infrastructure up there. If that makes sense.
Okay. I'm going to jump on the back of your question. Sorry. So we see Axiom. Yeah, they're going to build the lunar mission. They're going to put the stage at there. They're going to put one right there at the moon to let you to offload to get onto the moon. That's the ambition, and that's where they're going. Yeah. We see what happens with ISS. We still need EVAs. Do you still think we're going to need EVAs in the future?
EVAs when you go to interplanetary.
The extravehicular activity, where we've got the human has to go outside the vehicle and still do a lot of maintenance we're talking about still done by humans. In the reason why I mentioned something, I talked about the future spacesuit. That was we were working the spacesuit to take you outside and to do that maintenance. Do you think we'll ever get it completely robotic, or will we still need to have a human in that?
I think you still need a human. I mean, so you have the robot that fixes up part of the satellite, but then who fixes the robot? It's got to be the human. So you would need some human intervention, but the robot would take care of the robotic arm or whatever infrastructure is.
Yeah, it's going to solve it all. Don't worry.
It will. It will take care of everything, but the human aspect is still required. There's even the conversations with AI and machine learning. It's like taking out the human aspect, but that's not right. That's not natural. You need humans to be able to maintain and to continue. Yeah, to work on it.
Great, thank you.
So I wonder if you're able to give us an example of a recent or an imminent improvement in space situational awareness.
There are a few missions that Airbus is working on to make sure that they can capture any space debris, to either just bring them down to Earth. I can't remember the exact names of them, but it's either pushing to shoot out specific projectiles and move them away from the trajectory of spacecraft, or to push them out of that orbit and deorbit them into the atmosphere and burn them up that way. So I can't remember the exact names of them, but I do know that Airbus does work on a few missions such as that to tackle the issue of space debris and space situation awareness.
Okay, thank you.
Any questions from the audience?
Again, sorry. You mentioned about the use of digital twins and further software processes. How do you see a digital twin being advantageous over traditional finite element?
So what you do have with a digital twin is that all the imperfections within testing are added. So while in a finite element model, you have some theoretical representation of that imperfection, it's not fully representative of what happens in your testing. So obviously you have a finite element model, you go testing and then you check the two and you correlate them, and they're always a bit different. But with the digital twin, you do combine them to make sure, and you go through an iterative process through ML to machine learning and AI to make sure that they complement, that they work, and that you can rely on your digital twin to give you the answers that you need in the future. So I do see that digital twins are a better option than finite element models, but they are much more work intensive because you do require a little bit more correlation and working with different types of software and to get it all working correctly.
Any further questions from the floor? I have one question. Which of these do you find the most exciting and have the biggest impact?
I think as much as I think quantum is a good one. Just recently, Microsoft released their Major Runner quantum chip as well, which was interesting news, and they've been working on it for 20 years or something. But it's possibly the way the world is going to move slowly, not now, but it's probably quantum computing. And I mean, quantum still plays an aspect. All our phones and digital twin, like digital devices, are some form of quantum applications, but we do see more quantum computing possibly coming in the future to be able to. So that's probably something that's quite interesting to me.
there's no more questions. Thank you very much, Joe.
Thank you.
Yeah. Just be step channels.
Are we on? Fabulous. Whoosh. Fabulous. Hello. I'm going to be talking about material science, which is a little bit different to what the rest of the RAeS guys are talking about, but thought it'd be a bit interesting. And it's what I know most about. It's what I did at university, and it's what I do now as my role. So hello everyone. My name is James Miller, and I'm a materials engineer. I work at MBDA. The work I'm going to be talking about was when I was working at Kinetic. It was where I did my graduate scheme. I was a material scientist there as well, focusing on energetic materials analysis. And today I'm going to be talking about some of those energetic materials that I was studying and looking at the migration and degradation of some of the ingredients within them. So just to cover what we're going to go over quickly, what I'd like you to take away from today, so that you know what a composite double-base propellant is, how do they degrade, and what kind of materials tests did we do to confirm this, and what were the results. Of course, this presentation is unclassified, so there's no names, places, names of programs, or really specific numbers, but I'll go into as much technical information as I am allowed to. So just to start with, what is a composite double-base propellant? So composite means that it's got multiple ingredients within it. It's not a homogeneous one material thing. And the fact that it's double-based means that the fuel and the oxidizer within the propellant are mixed on a molecular level. They basically behave like rubbers, so they're highly loaded elastomers with lots of solids in them, which reduces their coefficient of thermal expansion. The common stabilizers used are nitrocellulose and nitroglycerin. Those are our flammable binders. And it's kind of a mix of lots of different ingredients that all have different functions, such as stabilizers, plasticizers, oxidizers, and binders. And the diagram we can see here, AP is ammonium perchlorate, which is a type of oxidizer, and it can exist in different sizes to provide different types of burn rate and thrust requirements, depending on the type of program that this is being used in. So these assets are made, and then sometimes they will sit in storage for 10, 20, 30 years before they are required. And over that time, they can degrade. They are made as a homogeneous product where all of the ingredients are dispersed evenly throughout. But over time, things like temperature, humidity, and even the sheer pressure of it, some of these weigh hundreds of kilos, pushing down upon itself can cause diffusion of different ingredients around the propellant material. We can see on the diagram the edge between the case liner and the propellant and the casing. It's the interface between two different materials, and this is a common area for failures, which we'll go into why and how in later slides. So the work that I did that we're going to be talking about today was when I was the test and evaluation lead on a program of work, making sure we're following the HSC licenses and NEQ limits within our labs. NEQ stands for net explosive quantity. Labs can only hold a certain amount of explosives at any one time, so it's sort of a supply chain issue of making sure the lab technicians have enough work to do, but they're not overloaded so that they have too much stuff in the lab at any one time that we're breaking our license limits. Doing the tests following different defense standards, those can be STANAGs, DEF stands, ASTMs, and the life cycle that the missiles would go through before they get to the lab is that they would undergo environmental testing, so that could be accelerated aging, increased temperature, humidity, or vibrational testing, so adding residual stresses, shake, rattle, and roll kind of things. And then they would be broken down into their constituent parts, following cutting plans, sectioned and machined, whether you're getting cutting specific 3D samples for mechanical testing or chemical powder for swarf for chemical analysis. So yes, the migration and oxidizer decomposition worsens our properties. This occurs at the edge due to the concentration difference. The plasticizers want to move to an area where it is less concentrated, which is close to the edge. The liner material can act as a sort of sink, and it can bond with that liner material so that it moves from the center to the edge. The diagram we can see here, imagine the green ones are the plasticizer.
So those are trying to migrate away from the bulk, and the lamellar barrier is the big high molecular weight binder getting in the way. And it needs to use its migration activation energy, or it needs to surpass the migration activation energy for this movement to occur. Now, spoilers, everyone's talking about physics. I'm going to talk about chemistry for a minute. This is a periodic table. I think we've heard of it. So what some of the chemical aspects of the plasticizers have that can cause them to migrate are things like polarity and molecular volume. So this periodic table is showing the electronegativity of elements. Fluorine, top right corner, is the most electronegative because it is a small element and it only has one more electron to become a full stable outer shell. Nitrocellulose and nitroglycerin have a lot of nitrogen in them. The binders are hydrocarbons, so they're just carbon and hydrogen. We can see nitrogen is more electronegative than carbon. Therefore, the nitrocellulose and nitroglycerin stabilizers will be able to form bond with the binder within the material, and it will increase the distance that those materials can migrate. The molecular volume is another chemical concept. All of the ingredients will have relatively similar kinetic energies. If we know that the stabilizers have a smaller mass, then we know we can plug in two of the numbers, and then we know the velocity will have the potential to be higher. Yes. So I'm going to talk about some of the tests that we did. In the top right is a diagram of the propellant. It's a cylinder with a hole in the middle, and then we've got a 2D diagram looking at it front on. The blue rectangles will be where we take the samples following those cutting plans to make sure that it's coming from the same point every time we do this test. And those are from different points across the radius, so we can track how it moves from the middle to the outside. One of the ways we can get chemical composition is with a technique called high resolution mass spectrometry. Just for time, I'm not going to be able to explain comprehensively how every technique works, but basically it uses that same kinetic energy principle. If we know the kinetic energy and we know the volume the velocity, sorry, by measuring how long it takes to get from the ionization area to the detector, every type of material has a characteristic mass, and then we can use that to work out what it is. And we can track how that changes sort of across the radius. Another test we can do is flash point. That's basically how flammable something is, the minimum temperature at which something will combust with air. The nitrocellulose and nitroglycerin are the really flammable bits. And if those are going to move from the bulk to the edge, then the edge is going to have more flammable material and the flash point will go down. In contrast, in the central radius near the middle, the bulk will have less flammable material and the flash point will go up. This can reduce obviously the homogeneity, which can influence burn rate and thrust requirements, which means things might not be able to reach the certain max speeds that we need for certain missiles to be used. Some mechanical testing we can do is DMA, dynamic mechanical analysis. This helps you find the glass transition temperature, which is the temperature at which a material will go when it's cold, really brittle and glass-like in behavior, to going above that temperature and it will behave more like a rubber. The graph we can see on the x-axis is temperatures, and this test would be called a temperature sweep. So you take it down to about minus 100 degrees with liquid nitrogen, apply a little twist to the bottom of the sample, and then measure the force at the top. At the start, when it's really brittle and doesn't want to bend, you see a really high amount of force, and then as you cross the glass transition temperature, it is able to absorb more of that energy, and the amount of force measured at the top will go down. And lastly, we have our classic tensile test. This could get us things like the ultimate tensile strength and Young's modulus. As that stabilizer moves around, the homogeneity is gone and it can become more brittle. So the Young's modulus can increase, but then it would take less strain for it to critically fail and fracture, so the ultimate tensile strength could go down. So the way that this can occur is, given enough energy, the materials can start to debond from each other. This can occur due to the difference in the coefficient of thermal expansion between materials that can apply residual stress within the propellant bulk. This can exist in the form of microcracks, and then over time, more kind of cycles of raising temperature, changing humidity can cause those microcracks to increase in size and grow into macrocracks, and that can eventually lead to fracture, kind of detrimental catastrophic failure. And then we can see this is a SEM image of that said fracture path. You can see the fracture path traveling across in between different particles of binder and plasticizer. And this is a form of catastrophic failure. So just to conclude, what have we learned? It's really important that we know about the compositions of these materials, as it enables us to design out issues that are occurring in ones that we're looking at now. In future designs, they'll have greater capabilities, less likely to fail in service, more value to the customer when we're making and designing and testing them. And as we come up with new technologies, propellants, even kind of the frame, if we're going to be hitting like Mach 12, Mach 20, then everything needs to interact with itself. So we need to be testing how those materials will interact in those situations to make sure that we are making sure that we're still providing that knowledge to new products. Thank you very much.
Are there plans to sort of achieve a relifing of an old propellant, something that's been in store a long time?
Potentially, if it still meets all the requirements that it was set out in the initial design specification, there's a potential for that. Haven't seen it in my experience, but I worked on this for about 8 months on one specific program. It was still being used, it was still deemed acceptable and good to go to the customer, but I don't know about things that are, say, 20, 30 years old, if they could be brought back from, say, at a certain point it failed. I don't think there's any coming back from that.
Okay.
If that answers your question.
Yeah, thanks.
I think you mentioned before about a shelf life. What it seemed like was it years or something you mentioned? How many years was it?
Well, some of them in the program I was on can sometimes be sat in stores for upwards of 10, 20 years.
Right, okay.
Before they are required by the customer to be used.
That's to store in a controlled environment.
Yeah.
Yeah.
Yeah. There is a case for spend more money on a more controlled environment so that there is less temperature change, less humidity change, but that all comes with added costs when, if it works now, why would we need to spend extra money? That's the.
If you already covered it, apologies, but looking at the chemical composition, the science behind the liners and the casings and those sorts of things, I assume that those need to be robust to at least ensure there's no migration into the containing structure, and that they have that life expectancy as well.
Yeah, different programs will have different costs. Some of them will use cheap sort of wrap it in metal. Some of them will go more carbon fiber composite way if they have more stringent sort of CTE requirements. But yeah, analyzing how that interacts with the propellant is definitely the bread and butter of this kind of work.
Okay, thank you. I'm going to pass on this one. Pass me really.
Thanks very much for the great presentation. Maybe 2 questions, we'll see how we go. I guess the silver bullet for that sort of thing would be monopropellants. Is that an idea that's kind of actively being looked into? I kind of have some base knowledge on like monopropellants in terms of rocketry, but whether that's applicable in this sort of scenario, I'd love to know. So, and it's potentially a second part. Materials compliance in this sort of area, kind of RAeS and ROche, and I don't know if those are things that are maybe like ring or fairly, but I'd be interested on that sort of side as well. So
yeah. So on monopropellants, this one being a specific composite double base propellant means that it is not monopropellant, and it will have lots of different ingredients, which makes it slightly more complex when studying the interaction and degradation over time. To my knowledge, there are monopropellant systems that are in use and do exist. They will come with, I guess, relatively more simple degradation characteristics and mechanisms because there's less ingredients to keep track of. And ROche and RAeS, I believe there are specific, what's the word? And the government, you fill in a form through RAeS and ROche to say this is a paramount ingredient that even while it might not be to a civilian breach compliant, it is paramount that it is used in this industry because it is so useful and important when used in this military asset, for example. So there are, RAeS was recently bought by MBDA, and they claim that all their products are REACH and ROSH compliant because they have received those justifications from the government. You say you can continue to use this ingredient if it is being handled safely. They have, audits to check that people are doing it correctly and safely and not contaminating anything, and making sure that, it is paramount for it to be used in the product, for it to have the required performance outcomes. Cool.
Mention the migration of what techniques are used to homogenize this?
Well, you design it homogeneously in production as best you can, and then try and maintain the temperature and humidity to minimize migration. There are obviously you can design out that happening. It's sort of a balance between the stabilizers in its name stabilize the material, but if you have too much of it or a higher percentage, then there are more low molecular weight objects which have the capacity to move around and become less homogeneous. So it's a play off between you want it to be stable, but you don't want it to change in its homogeneous structure. So there are lots of different types of compositions kind of playing both of those two sides that provide different outcomes. So both are considered, but yes, it's a valid concern.
I think it was on the material properties side or mechanical properties side, you had how the propellant was stored, and there was a little bit in the middle you noticed that was empty.
Diagram?
Yeah, on the diagram. I'm just wondering, is that to do with extending the shelf life? Like why
is there a hole in the middle?
Yeah, why is there a hole? It might not have more of the propellant.
That's where the bloom comes out.
Could you not just like the bottom? Is that?
Well, you do like the bottom, and then it will slowly burn up from the bottom to the top. It will have a characteristic shape. They're not all cylinders. Some of them have more complex designs because you need different flight profiles and surface area on the 2D cross section. But yeah, it's to let the thrust out of the missile.
Yeah, well, perhaps a bit of a neat one. On the mechanical side, with the gas transition, there's TAM delta there. Is that particularly important to the LC track, or is it mainly for?
It's still
divided by loss. It's a way of saying, you could say either the peak of the tan delta is the glass transition temperature, or the peak of the loss. So the top of the blue or the top of the black. Depends on the standard you use. We use the blue one. It's not hard. I used to do this one. Nope.
How does the geometry of the cross section affect the shelf life and also material properties?
Material properties, I'm not too sure. It would allow it to be in contact with more air, so maybe there would be more migration that way. But that is in the central rather than at the edge. The edge acts more like a sink than the middle does. I think the materials at the edge are a bit less stringent than the ones in the middle for like limiting migration. And sorry, what was the other one? Material properties. Oh no. Yeah. Okay. Yeah.
But yes, it certainly does have an effect. Thank you.
Okay.
All good to go. Good evening, everyone. Thank you all for coming.
My name is Himanshu, and I'll spend the next 10 minutes talking to you about the Kessler syndrome, the orbital debris issue that we have going on currently, specifically in the lower Earth orbit, and what that means for the future of space exploration. Now, to start off, I'd like to define what exactly is the Kessler syndrome. So this is a term coined by Donald Kessler in 1978. He is an American astrophysicist, as well as a ex-NASA scientist. And the easiest way to describe the syndrome is to imagine a domino effect in space where orbital debris is colliding with each other, except this domino effect doesn't quite stop. This is a self-sustaining loop. So this is something that will continue to go on and on without intervention. This is a global risk to every single satellite that is in the lower Earth orbit, and that includes the majority of satellites in space. And so these provide vital functions, which we will be going on to shortly. Debris also has a very long-term impact in space. So orbital debris has shown to be present in orbit for up to decades. And so not only are you impeding the current space operations, but future space operations for coming generations. Now, it is also a proposed solution to the Fermi paradox, which deals with the sort of high probability of there being extraterrestrial life due to, as well as the lack of evidence that we've ever come in contact with any. And so if Kessler syndrome is severe enough, it could be proposed to enclose whichever planet there is operating in and essentially act as a barrier to use that orbit or to leave that orbit. And so a very edge case scenario, this could be something that limits any spacefaring civilization after a certain point of development. Now that we've introduced the Kessler syndrome, I'd like to go into some of the mechanics that actually fuel this effect. So this is a feedback loop that consists of reinforcing and balancing loops. And there's only one balancing loop in this, in that it balances the adverse effect of the Kessler syndrome. Active satellites, when are involved in collisions, no longer become active, and as such, you have less active satellites involving collisions. The rest are, in fact, reinforcing the Kessler syndrome. So inactive satellites, when collided, will break up into smaller inactive satellites and thus cause more collisions. Debris size tends to segment over time. So when you have larger debris colliding with each other, this will become medium-sized debris and eventually smaller-sized debris. Now, in the early stages, the larger size debris collisions are the ones that dominate sort of the collision potential. And then going onwards as time progresses, the smaller fragments are the ones we should worry about the most. And so it seems very straightforward, but this constant loop of collisions, debris, and thus more collisions is essentially what Kessler syndrome is that it's this collision little cascading that, if not kept in check, will run amok. Orbital decay is something that does balance this syndrome in that debris tends to naturally deorbit and upon re-entry into the atmosphere, burn up. However, this happens at a rate too slow to be deemed significant, and as such, Kessler syndrome is still a very real problem. Speaking of which, now I'd like to highlight why we should be concerned. Why is this a problem to any of us? And so, like I said earlier, there are vital systems in low Earth orbit, which spans from sort of 160 kilometers to 1,600 kilometers. This region encapsulates most of our telecommunication systems, as well as Earth observation and surveillance. In fact, the Hubble Space Telescope is located in low Earth orbit. There is no escape from debris in that if it's coming at you, it's not going to swerve to make way for you. And so it's on the onus of whichever satellite to perform intricate avoidance maneuvers to avoid the potential damage. And this also decreases the potential spacecraft lifetime, as more collisions over time will degrade the spacecraft casing. This is a threat to human presence in space. So as mentioned earlier, EVA is something very useful in terms of repairing spacecraft during its lifetime. And with there being more debris in the low Earth orbit, this becomes a more dangerous scenario. The longer we wait, the more sort of complex solutions and costly solutions we will have to come up with to battle this problem, as this is something that will grow on an exponential level. This is a global dependency in that space is a shared commodity, and as a result, globally, we are dependent on space. This means that the solution that we should be chasing should not be something that one individual or one organization should be chasing alone, and rather it should be a unified front. I'd now like to talk to you about some historical incidents that have happened to exacerbate the syndrome or have been caused due to the syndrome. So to start off with, 2007, China performed an anti-satellite test, and this involved destroying Fengyun 1C, the defunctional weather satellite, and this produced over 3,000 new debris fragments, many of which are still in low Earth orbit today. This was one of the largest single debris events, and events like this do largely exacerbate the speed at which Kessler syndrome is catching us. Now on to Iridium-Cosmos collision. So in 2009, the US active satellite Iridium and the defunctional satellite Cosmos collided, and this was something that people could have seen coming. Iridium was projected to have a closest approach to Cosmos at about 584 meters. Now, for a distance that close, you would expect some sort of precaution, some avoidance maneuver to be performed, none of which was taken forth. And so when this closest approach occurred, Iridium stopped communicating, and in its place, a debris cloud was observed. And so over 2,000 new debris fragments were created in this collision, and this was the first accidental collision of two satellites in space. All of these go to show that Kessler syndrome is not just a theoretical edge case, but very much early signs of something we will have to tackle either now or later. And so this is a visual of how the debris in the aftermath of the Iridium-Cosmos collision evolved over time. So this was all very bunched up together in the same sort of orbit, but then over the course of time, it has dispersed to encapsulate sort of the face of the Earth. And so you can see that it is not just the specific orbit that the satellite was in that was affected, but in fact, far more than that. There was a video, but I don't think I have time to go through that. This was just to depict the present situation of the orbit. So over 36,000 trackable objects are larger than 10 centimeters are in orbit, according to the European Space Agency. An estimated 1 million objects between 1 to 10 centimeters are also present. These are too small to track, but far too important to ignore, since these impacts can have very severe effects on the satellites that we have. Most of this debris is concentrated in the low Earth orbit. This is due to mostly how cheap it is to get satellites into this orbit. And new satellite constellations, such as the aforementioned Starlink, only add to this effect since they take up so much space in the low Earth orbit. It just increases the collision potential and is sort of begging for an adverse effect. An average of 1 to 2 collision avoidance maneuvers that are unexpected occur per year, and this value is seen to be rising. And so clearly this is something that we need to address. And so this is a plot to depict the sort of population of debris across the altitude of low Earth orbit. And you can see there's a clear peak around the 600-kilometer region, as well as the 800-kilometer region. And the plot on the right depicts sort of how many payloads are owned in that orbit according to the sectors, essentially. This is a more easy to interpret plot, which very clearly shows an exponential trend of debris growth that we have recorded. This is not even going into any predictions. And over there, we have the distribution of debris across each orbit. So there are two paths forward here. If we do nothing, orbital congestion will continue to accelerate exponentially in the low Earth orbit. Kessler syndrome will kick in, and we will lose orbital access severely. Essential services will be disrupted, and space then becomes a liability as opposed to a commodity. It's something we can use. If we act now, active debris removal solutions can curb this cascade. Missions such as ClearSpace and ELSA-D. Smarter satellite design to mitigate these issues before they even come into play can also be done to mitigate this. Global policy coordination, like I mentioned, this needs to be a unified front as opposed to individuals and organizations. And performing sort of the mitigations to this Kessler syndrome will just result in a sustainable space economy for the foreseeable future. And so this is a plot by NASA's Legend LEO to Geo environmental debris model. Through Monte Carlo simulations has predicted that with PMD, which stands for post-mission disposal, the population of orbital debris will only continue to increase. However, if we include ADR, which is active debris removal, at 2 objects per year and 5 objects per year, we can see that trend to very vastly go down. And it is still increasing, but we have this in control if we act now. Now, potential solutions, like I mentioned, the aforementioned ELSA-D is the end-of-life services by Astroscale demonstration. And so Astroscale is a Tokyo-based debris removal company, and it essentially involves 2 satellites, a servicer and a client. The servicer is designed to safely remove debris from orbit. The client serves as a piece of replica debris, just to have a faux piece of debris for demonstration purposes. And it uses a magnetic capture mechanism to dock the client onto the server and then safely re-enter orbit. The mission concluded in early 2024, and it is a great proof of concept for where this active debris removal technology can go. The ClearSpace 1 mission is led by the Swiss startup ClearSpace, and it is funded by the European Space Agency. And so this is something in the planning stages, but it is, again, another great prospect of there being money in this sector to remove debris safely. And it is something that was preceded by previous missions that didn't come to fruition. Now, to wrap up very quickly, the key takeaways from this presentation is that the threat is very real of Kessler syndrome, and it is accelerating day on day. The collisions fuel further collisions, but the tools exist. We do have the technology. What we need to do is act now. This is a shared responsibility amongst nations and organizations. Space is a global commons, and we need to work together to protect it. This is why stakeholder collaboration is essential in this field. And future generations, like I said, are dependent on safe access for orbit, for their own scientific development, their own communication, and their own exploration. And so it'd be a disservice to ruin that for them before they can even get there. Thank you very much for your time. I'd love to field any questions.
Yeah. So you're describing something that sounds like climate change.
Yeah, it's very analogous to climate change.
Has there been a debris COP?
Not something between nations, unfortunately. It's between organizations at the moment. The UN currently relies on voluntary compliance, in that if an organization performing a space mission is compliant with the sort of standard deorbiting after 25 years to make sure the orbit is not cluttered, then perfect. But even that compliance is not at 100%. I do have a figure here depicting the sort of compliance across smaller payloads, slightly larger payloads, and you can see that the larger the payload gets, there is a far lower compliance rates. And in fact, across sectors, shamefully, defense is one of the slowest growing compliance sectors here. But you can see some improvement. Sort of the European Space Agency's push for active debris removal and compliance to that 25 years deorbiting is starting to work. And constellations such as Starlink, for example, are actually very compliant with that post-mission disposable planning stage at the least. We'll see how that ends up.
So the UN is doing something.
For voluntary compliance, yes.
So we talked about Kessler then. So the assumption there is that we never lose any energy. Yeah. Is that true?
Yes.
Zero energy loss at all.
In that the debris in a collision, I see. Okay. So over time, debris does tend to lose energy, and as such, the inclination of all debris in orbit will start to align with the equator.
Right.
And so over very vast sort of periods of time, you'll see an effect like Saturn possesses right now, in that its rings of debris have gone through that evolution. But that is a very, very long-term effect. In the short term, that's something we can't really consider.
And the deorbit, do you see a position in the future that we will regulate to actually to bring back?
I would urge on it, if anything, because it is very much analogous to climate change of our atmosphere. Space is a shared environment. And as a result, there need to be more strict compliance measures, more reprimands for companies that don't comply. There needs to be more incentive for companies to, for one, perform active removal and also take care of the satellites that are already there.
Okay, thank you.
Thank you.
I think you mentioned a number like 36,000
Yes.
items, something like that.
Yeah.
You're not going to tell me we're going to try and recover those, are you?
No. So that's across all orbits. Yeah.
Is the idea then that preventative try to...
Precisely. I think if we go back to this plot here, you can see that this is a preventative measure. At no point do these plots go down.
Yeah.
This is something to control the uncontrollable, Kessler syndrome. And it shows that if we act, we can control it.
Okay. Over to the audience.
I feel like it's kind of maybe already been highlighted so far. Again, thank you very much for the great presentation. It's really about that flow down then from voluntary compliance from the EU towards space agencies such as ESA, JAXA, and various NASA services that you mentioned. What if you might suggest kind of what that might look like? Is that kind of regulation in order to have something in orbit, it must already kind of have these active measures.
So those measures are not as strictly placed, but to a good extent already followed. So the 25-year end of life disposal kind of thing essentially says that move your satellite into a graveyard orbit or deorbit it for re-entry and burnout. And so currently that is being implemented, but what I was hinting at in terms of there being more reprimands and more stricter regulation of, for one, what you're putting up there and also what you're doing to clean that orbit. I think that is something that should be focused on far more and is currently missing.
Why the oscillation? So this is something I looked up just today.
So it is in part. Sorry?
It's an artifact of the model.
Not quite. So the Monte Carlo simulation is a random sampling method. And so, yes, it relies on random numbers to generate its predictions, which over time average out to a sort of balancing effect across them. But this is also dependent on solar cycles. So the sun follows an 11-year solar cycle, which essentially cycles its solar activity. So the higher the solar activity, the higher the atmospheric drag, and the higher the orbital decay. So presumably here, you have a higher orbital decay, and as such, debris is being removed naturally.
Are you aware of any initiatives to remove anything in GEO or graveyard events?
Not that I know, but yeah, so not that I know, but I'm not aware of any need to do so as of yet, since these are very expensive distances, and as a result, there hasn't been any congestion issue as of yet, and hopefully not for the foreseeable future.
So it's been an absolutely fantastic evening. I've really enjoyed that. Some really, really excellent talks. So I would like to say, so on behalf of the Aeronautical Society as a whole and the Stevenage and Luton branch in particular, thank you all very much for coming. Thanks to our speakers for providing some fantastic, I can call it entertainment, I think. So thank you for that. Thank you to the audience for coming along and taking your time out to support this kind of thing. I think it's vital that we can support early careers people and young people from across the local area. Thank you to our judges for giving up their time to support this. So we couldn't do this without yourselves. And importantly, I would like to say, as chairman of the local branch, an enormous vote of thanks to the sterling effort of the branch committee members. So Louis has put in incredible amounts of effort to bring this all together, to get us all in the room together today. So a round of applause for him, please. And additionally, Will has done fantastic work once again supporting us for everyone who's on Teams. So thank you for your attendance, those of us who've joined digitally. But yeah, Will, again, a fantastic member of the society and couldn't do it without him. So thank you all again. Thanks for the evening.
Can I have attention, please? I'm glad to announce that we have a winner. So if I could, so first, can I get a round of applause, please, for third place? We have.
Okay, so I think from my perspective, I thought to thank you very much, everybody, for what I thought were great presentations. I thought they were very engaging. I thought, it was, I thought, very brave for a lot of you, and some of the topics you were out of your comfort zone. I could see that, and you did a great job. So thank you very much. And I thought, whether it was the standard of the visuals, your oral presentation, all were great. So we had a bit of a debate. We all scored. It was tight in places, but we had we tried a few times and the smoke went up, and yeah. Anyway, we got there in the end. So in third place, William Nichols. Congratulations. Well done.
Cheers, thanks, guys.
In second place, James Miller. Yeah. In first place, Himaji. Congratulations. Okay, I'll go with you.
Congratulations, everyone. Congratulations to all our competitors. It honestly has been a phenomenal day. I've really enjoyed it. I can say everyone else here has really enjoyed. So all should feel really proud of yourself. Himanshu, you've won our estated Aeronautical Society Eagle. So you have the opportunity to now go to nationals. Tony, if you'd like to present.
Is it space debris fine?
Feels